All right, so we are back from the break, and I want to go straight into parts per million. So, first question on parts per million is calculate the parts per million of 12 fluid ounces of solution comprising 20 MEQs per liter of calcium chloride, which is CaCl2, and the molecular weight of 111. So, parts per million is measured in it's a ratio of either weight per weight of the same unit, so that could be milligrams per milligram of another thing, or milliliters or liters per liter. They just need to be an exchangeable amount of, they need to be dividable to make an effective ratio. You can also have like milligrams per ml, things like that, just because you're looking at, it would be one, or like if it was 2 parts per billion, it would be 2 milligrams of lead. Let's say like there's lead contamination in the water, 2 milligrams of lead per million ml of water. That's just what the ratio is saying. And this actually works great. Should have been using this the whole time. Yeah, so it's mostly just a ratio. So in the question, we have 12 fluid ounces, and we have a solution 20 MEQ per liter at 20 milliequivalents per liter. And for the parts per million, we need to find out how many milligrams, or just how much calcium carbonate we actually have in solution. So to do that, we go 20 MEQ per liter. We have 12 fluid ounces. 12 times 30 is 360. So 360 milliliters at, let's rewrite this, 360 milliliters, and we have X milliequivalents equal to 20 MEQ per 1,000, because 1 liter is equal to 1,000 milliliters. That. So that is 0.02. Let me just double check that. Yeah. So that's 0.02 milliequivalents per milliliter times 360 on each side. So it goes bam, bam, and then 0.02 times 360 is 7.2 is equal to X MEQ. This is just to cancel out the units of milliliters, so we just are left with our milliequivalents. That being said, we now know how many milliequivalents, but in order to do a proper parts per billion, we need to know the amount. Yeah, we need to know the amount. So 7.2 MEQ is equal, and if you recall, our MEQ equation is MEQ is equal to milligrams over molecular weight times valence is equal to 111. That was one of our initial values. 111. What was our milligram? Oh, we're trying to find our milligram amount. times valence. And what is the largest charge in this equation? It is calcium, so we have a charge of 2. So multiply that over to the other side, 7.2 times 111, 799.2 equal to x milligrams times 2 valence. Divide the entire equation by 2 to get rid of that 2. 399.6. I want to make sure my head wasn't in the way. 399.6 equal to our milligrams. Yeah. And from here we have to go fluid ounces, parts per million. Okay, cool. Sorry, I was just thinking of where I need to go next. So we have 399.6 milligrams is yeah, so we actually can just work off of that milligram amount. I'm going to transfer this into grams, so I'm just going to move it 3 decimal places over. So 0.3996 grams per 360 grams of water, because our amount again is that 360 ml, and 1 ml of water equals 1 gram of water. And because we're trying to get parts per billion, we cancel out the grams. Parts per million, not billion, sorry, times 1. So divided by 360. That times is equal to 1, 1, 1, 0 parts per million. So that's saying that we have 1,100 parts of calcium chloride in solution per 1 million particles of water. Or parts of water, not particles. Excuse me. With that one done, maybe you can... This thing's a tank. Should have been using this. For the next problem, next parts per million, so next parts per million, while working at the mercury factory last weekend, you accidentally poured 1 quart of mercury into the water supply, now totaling 2,760,000 liters. What is the parts per billion of this solution? So again, let's go back to our gallon amounts, which is important, as I've said. So 1 gallon equal to 128 ml, not ml, who am I kidding? Fluid ounces times 1 quarter over 4 equal to 32 times 30. So that's 32 fluid ounces times 30 milliliters per fluid ounce is equal to 960 ml. I don't know off the top of my head how many, like, I can tell you now that it's 32 fluid ounces, but I wouldn't know how many fluid ounces are in a quart, just like from the dome. So we have 960 ml of mercury. Talk about a horror story. And you pour it into 27,000 or 2,760,000 liters. So just to make things easily convertible, I'm going to turn that 2.76 million liters into ml, just so I can cancel out that. So that'll be 2760, 1, 2, 3, 1, 2, 3, times 1 billion. And this is the important part. And the important part is per billion. Watch out for the billion part. So yeah, you add on 3 more zeros to the end, and yeah, you just carry out that function. So 960 divided by 2760, 1, 2, 3, 1, 2, 3 ml times 1, 2, 3 equals 347.8. 3 parts per billion. If you're doing something like adding in, so her questions on her worksheets are probably the most loyal to what you'll see on the exam in terms of parts per billion. But just as like a concept, it can be helpful to recognize that parts per billion is a ratio of two things together. Because sometimes, like for me personally, I didn't understand that for a long time until someone explained it to me as it's parts per billion, which like it's in the name, but I didn't understand what that meant until it was spelled out to me. So moving on to specific gravity, and I'm moving a little bit quicker through this segment because I feel like it's kind of like settled into the tone and you've started to get a feel for the equations, and just like it's kind of like warming up. The more you warm up, the better you can like function within the math. It's like you start seeing the numbers fly by. Specific gravity. You have 100 milliliters of ethanol, specific gravity of 0.789. How much does it weigh in ounces? This might be similar to a question. So we have 100 ml ETOH, ethanol, at 0.789 SG. So with specific gravity, it's 0.789 is equal to, where specific gravity gets confusing is the like equivalent weight of water part. That is like kind of a pain. So you take the volume, like whatever your volume is, you just use that. It's just, if it's in ml, the equivalent weight is 1 to 1. So milliliter is equal to 1 gram of water. Easy. That's the way that I think about it. I see the volume. I say, if it's in milliliters, I can just go straight into grams of water because the density of water is 1 gram per ml. So 100 ml is equal to 100 grams H2O. And we're trying to find how many milligrams of ethanol do we actually have. So that's 0.789 times 100 is 78.9. Done. Oh, how much does it weigh in ounces? Not done. Last value. Last value is ounces. And ounces. Oh man, 78.9 milligrams. No, grams. Holy hell. Long day. 78.9 grams. And there's 30 grams per ounce. So 78.9 divided by 30. I don't know why that took me so long to like get through my head. Now I gotta be the one to like do the Quizlet with all the conversions. That's a throwback to the last video. Anyway, 2 pounds propylene glycol, initial value 2, specific gravity 1.039, 1.039 is equal to 2 pounds. How many 15 ml bottles do you need to contain all of it? So this is the reverse of the previous question. We have the top value, but we don't have the bottom value. So mg, but again, not mg. This bottom value is just going to be equivalent to the actual volume that that amount of propylene glycol will take up. So I'm just going to put that in ml. And then 2 pounds, 2 times 16 is 32, I think. 32 ounces times 30, 960. 960. And then we have to do weird cross multiplication where we kind of trade these two. So multiply x to both sides. That gives you 1.039x equal to 960 divided by 1.039. 3.97. And so that would be our intermediate value. Our last value is going to be how many bottles does it take to get to 15. So that's going to be an ml divided by 15 ml in 1 bottle. Divided by 15, 61.59. Now, if you recall, we cannot have roughly half of a bottle because that would mean we just cut the bottle in half. That's not good. So we just round it to 62. A question may or may not include something like that. These are all pertinent questions and similar to ones that I don't want to deal with the eraser. Might see. I get the feeling that you will. But this is a cost calculation problem, and there are a few moving parts to it. I'm going to try and like do the same thing that I would have and did do for it, which is this method, but I think of it in kind of like a ping pong. You know when Forrest Gump is playing ping pong by himself? It's like that, and it just goes like faster and faster and faster. So quart of mineral oil is 128 times 0.25 is equal to 32 times 30 equals 960 milliliters. So that is one of our initial values. recipe calls for 478 grams of mineral oil. SG 0.9 is equal to 478 on the top, divided by ml on the bottom. 829, 8.29. We now have all of our initial values kind of connected to one another. And now we do our cross multiplication again, which just leads to 0.9 divided by, where's my calculator? 4.478 divided by 0.9 is 531.11 repeating is equal to ml, and we have a total of 960 ml. 960. So these two are equal. 960 is equal to 829. We're making a ratio to find out how much it costs, because that's our final, that's the last value. That's the last value. We need to find out how much it costs. So 0.55 times 8.29, 457. 4.57. And because this is in cash, wrong way, 4.59. That's where you got to watch your decimals. Decimals is just 2. So, yeah, that is the speedy version of that problem. And then we're moving on to, I think, nutrition. Yeah, nutrition is next. And nutrition, with the added caveat of the new calories, is a pain. It really is. And it wasn't fun to begin with. So with nutrition, you really do need to have that chart of caloric conversions memorized. It sucks, but you have to. Excuse me. I'm sorry, but it's just, you gotta. A TPN order comes in for 1 liter containing the following 7. So in TPN orders, the DILF-D is it's reversed, because some of the first things that you're going to be reading is like the actual order. So 7% dextrose is our goal, 10% lipid emulsion is our goal, 2.3% amino acids is our goal. And then you're given your shelf, which is your starting values, which is 20% dextrose, 30% lipids, 8% protein, and purified water for injection. How much of each solution do you need? So we are starting out with 20 grams per 100 ml dextrose. Let's do lipids next. 30 milliliters per 100 ml of lipids, because if you look back at that chart, the lipids, when they're injectable, they're given as a lipid emulsion, so it's measured in mils per mil, or yeah, mils per mil. And it doesn't really mess with the actual math, but it's just something to keep important when you're doing your units. 30, and then amino acid count is, what was our start? 8%. So that's 8 grams of protein per 100 ml of water. This is the chart that I make myself when, like, I'm in exam. So I have initial and I have last. IL. So for initial, we have each of these. Our last is a goal, and the last is also measured in a liter because they're requesting a 1 liter bag of this. Is 7, I want to say. Yeah, cool. So 7 per 100 times x over 1,000, or equal to. So 7 over 100 is equal to x over 1,000, and I do all of these values together kind of as one thing. Our lipids, we're looking for 10%, and we have 10 per 100 is equal to x over 1,000. And then amino acids, we have 2.3 over 100 is equal to x over 1,000. So it's all x over 1,000 because the liter bag that we're making is 1,000 mils. So we do all of that. Our goal is for here 70. So this would be the total amount that's in the final 1 liter bag. So we have 70 grams, 100 ml of the emulsion, and 23 grams amino acid. And what I do for these kinds of questions is I take these numbers, 70, 100, and 23, and I divide them by our initial. So 70 divided by 20, excuse me, 70 divided by 20, 3.5 is 3.5. Let me make that a bit bigger. 3.5, 100 divided by 30, it's 3. Yeah, 3.33 repeating. Sorry, I like zoned out for a second. 23 divided by 8. 2.875. So these are all our multipliers, and then we multiply each of them by 100. So times 100 times 100 times 100. So 350, 333, and 287.5 is the total volume of each solution that we need. So yeah, and then you add all those together. So 287.5 plus 333.33 plus 350. So all three of those together, you get 975.33. Subtract that from 1,000 because that's your milliliters. So you get 24.67. That sounds right. I think. Maybe. Wait a minute. No, it doesn't. 287.5. Okay, yep. It's 833. I misread the 3 as a 8 as a 3. So that minus 975.83. 975.833. 2716. 7. I'll just call it 1.7 for rounding, ml water, because you also have to factor in how much water you need. And adding on to this question, what percent of the total calories, note the big C because big C means kilocalories, are coming from the amino acids? So for each of these, we take, this is why this chart is helpful, because it kills two birds with one stone. You get 70, multiply it by your factor of carbohydrates. I forget. 3.4 calories per gram. So 70 times 3.4. 3.4 times 70. 238. And this is also going to be on the document as like it's all written out. Yeah, 238. And 100 times 1.1 ml for lipids is 110. And then amino acids, we have 23 grams times, I want to say 4. Yep, plus 92. So 110 plus 92 plus 238. 440 total calories. And because we're looking for like our final, our last value is last value. Why can't my eyes focus? Jesus. Okay. Amino acids. Whew, that was bad. Total calories 92 divided by 440. 20.9%. I'm just going to leave it as 20.9%. Just because easy. Oh boy. Isotonicity. Isotonicity is kind of a pain because we were never taught it, and neither were you guys. So it's a completely new problem that we've had zero instruction on how to do. And it's like up to us to save the day for ourselves. So isotonicity is, generally speaking, it's trying to get you to a solution that is equal to body like osmolarity. It's trying to make it so that whatever solution you're going to put into the body isn't going to explode or shrink cells, and it's just trying to minimize those like adverse reactions that can happen. The struggle comes in is when you're adding drugs to that solution, you need to alter the amount of sodium chloride or boric acid that you use to isotonify the solution. And so you need to change that depending on what drugs you add in, because each drug contributes differently to isotonicity. Some contribute way more, some contribute way less, especially depending on like molecular size, how many like salts it forms, and whatever. That's like beyond what we actually need to know. But to determine how much salt you need to add, you need to take the total amount of sodium. So like, let's say you had 50 mil QS water. How much sodium chloride would it take to make that isotonic? So how much would it take to bring it to a 0.09%? That's 50 times 0.009. 4.0 whatever equal 0.45 grams NaCl. With that, that's how much it would normally take to make it isotonic. Then you bring in other drugs and you need to make them equal to salt so to this salt, to be able to make them talk to each other. You need to bring them down to the same equivalency level, and that's where E value comes in. E value is a way to turn the isotonicity that things like, what's a question? Morphine sulfate, that's the first one that we're going to do. How much is morphine sulfate equivalent to in salt? And that number is 0.14. But it's just kind of asking how much salt is it equivalent to. And then you take all of those together of all the drugs that you're adding, you combine them together and you subtract from this. So sum of like yeah, milligrams times E value, or is it MEQ? I almost want to say it's MEQ, but I don't feel like that's right. Hold on 1 minute. Okay, so Ashley was wrong on both counts of that. You use grams to times the E value. And then you add them all together, subtract from that, and then you get how much salt you need to add. So this part where you're getting the sum, it's like saying this is how much the morphine sulfate is adding to the isotonicity of the solution. And then you need to find out how much more salt you need to add to make it isotonic. It's like this, the difference between the 0.45 and the sum of all of the grams multiplied by the E value is how much salt you need to add to bring it back up to that isotonic value. And something that I'm going to cover in like the problem, or one of them, is she's going to ask you about boric acid. It's important to note. And boric acid is another way to bring up the isotonicity. And one molecule of boric acid is worth half of, like one group of boric acid is worth half of sodium chloride. Roughly half. It's like 0.52. So whenever you get this difference, if you're working with boric acid, she has like this weird long equation where it's like you do the exchange of values. That doesn't make any sense to me at all. I just divide by 0.52 here. And that tracks. So if you're asked to convert to boric acid, first you find out how much salt you need, and then you divide by 0.52. And a good way to like conceptually think about that is that you need twice the amount of boric acid to do the same work as 1 sodium chloride, roughly 2, because you're dividing by 0.52, which is almost the same thing as multiplying by 2. Whatever. Into the problems. Oh, I'm so sorry, whiteboard. You're asked to prepare 30 milliliters of a solution containing, so 30 milliliters, 2% atropine, 1% morphine sulfate. Okay, cool. And this is using salt. And I didn't finish this problem. It's supposed to say how many milligrams or how many grams of salt you need to make this solution isotonic. So 30 ml times 0.01 and times 0.02 for the atropine. That gives us 30 times 0.3 and 0.6 grams of atropine and morphine sulfate. So we now have our grams, and so we then multiply by our E values, 0.14. So this is another good time to just conceptually think 1 gram, so 1 like unit of morphine is only worth or 1 unit of, oh my god, 1 unit of sodium chloride is worth 0.14 for morphine. So morphine is just worth like way, way less than the salt. Yeah. So that's just another thing to, like, you might want to, as you're going through this, maybe for the first time, think, so this is what these E values are actually saying and like what they're equivalent to. So we have 0.3 times 0.14, 0.042 grams NaCl. So 0.3 grams of morphine is only equivalent to 0.042 grams sodium chloride. I guess that would have been a better jumping off point for that. So then we get 0.6 times 0.13 equals 0.078. Add those two together, 0.42, total of 0.12 grams, 30 ml. How much sodium do we need to make 30 ml isotonic? 0.009. Oh, there we go. Is 0.27 grams. Then you subtract 0.27, or you subtract 0.12 from 0.27, and that gives you 0.15 grams NaCl. And if this question were saying how much boric acid would it take, you would just divide that by 0.52. Yeah. And then let's just try regular. Yeah, whatever. Hindsight 2020. And then 60 ml. 60 ml of our next, this is the next problem. Dental numbing agent containing the following mixtures: 0.05% epinephrine, and there's 10 milliliters of that are already isotonic, and 4.5% lidocaine. And we're using boric acid as our stabilizer in this one. So the already isotonic part is something that is also kind of trippy, because those 10 mLs are already isotonic, so you don't need to calibrate those into your how much do you need. So when you're doing the problem for how much sodium chloride do you need to make this solution isotonic, you take your 60, subtract off however much is already isotonic, because the salt is already there. You don't need to account for the salt that's already in solution that came with that epinephrine when it was added in. And that also means that you don't need to account for the epinephrine. It just kind of like sits there on its own, because again, it's already balanced and accounted for. So take 50 ml, 50 times 0.009, wrong way, 0.45 grams NaCl. Okay. And also, this is the last problem for this video. So, gonna be done soon, and then we can have another little break, and we go into the final video. And so, for 0.5% lidocaine. So when you're doing, and this is the part that kind of got me really confused at first, when you're doing the like concentration calculation, how much lidocaine you actually need to add, or like how much lidocaine is in the 60 mils, you do use the 60 mils. You don't use the 50. So 60 ml times 0.045. 60 times 0.05. 2.7 grams lidocaine. And lidocaine is worth 0.2 of salt, and that gives us 5.5. Oh geez, I might have paradoxed this one. 50. Hold on, 1 second. Okay, I just read it wrong. The actual thing is 0.45% lidocaine. So it's 0.045% lidocaine, which means, let me just erase this bit. So 0.0045 lidocaine times the 60, 5 times 60 gives us 0.27 times 0.2, because that's our e-value. That's 0.2 equals 0.054. There we go. Yeah, that tracks with before. 0.45. Let's do this in a separate. So now we're taking our 0.45 grams NaCl minus 0.054 plus 0.4 is 0.396 grams NaCl to make it isotonic. But since we're adding the boric acid instead of salt, 0.52. That's it. And then, so let's just divide by 0.52. 0.76. Yep, there we go. I'm going to say that math was not lining up with previous math. But we figured it out, and that's why you follow DILF-D. Follow DILF-D, and you won't go wrong. I was just getting ahead of myself. That is going to be it for this video. The next video is going to cover the miscellaneous math problems. The miscellaneous math problems, I think, are the most loyal out of all of these to the questions that I remember from the exam. All right. Bye. Have a good break.